think the skin is visible, right?
Yep.
So actually, I'm trying to synthesizing this sodium antimony selenide structure. So I
Hmm.
think the predicted structure is like something like trigonal or something, and it's like thermal conductivity is 1.3 or 1.7. But
Okay.
in ICSD, I found the structure is reported with like cubic space group.
Hmm.
So it's like the same as the NaCl structure type with sodium and antimony is randomly disordered.
Hmm.
And so from literature, so it shows there is like two phases. One is monoclinic alpha phase, and another one is the disordered cubic beta phase, so which
Okay, so this is
has
this is interesting, right? So it's a rock salt structure,
yeah.
rock salt, right?
Yes,
And then the sodium and the antimony. Okay, I see. It sits it on the cation side, which is 50-50
yes,
disordered.
yeah,
Interesting. And surprising that sits in. Oh, wow. Okay, okay, I see. Got it. Okay, okay. So it's basically like, but how come 1 plus 3 plus? This is very perplexing to me.
yeah. So need to.
Cannot picture it. Like, for example, like
Hmm.
if your valence is the same and the ionic radii is the same, you can imagine that the same site is randomly occupied. How is it that this sodium and antimony are quite different, right? Even then, they
Yeah.
sit in the same site, bonding
Maybe
to
some
selenium.
degree of some degree is not fully. Is it uh fully disordered?
Yes.
50-50.
Like
That has to
fif-
be. Because you see, it's basically like saying it's an NaSe and SbSe or something. But here, the selenium cannot just be, it's some funny bonding, right? Because selenium is not just a 2 minus, because there's a sodium 1 plus if it's a rock salt structure,
I
which is
mean,
bonding with the selenium, separate differently from the antimony that's bonding to the selenium. Is it correct? That's what I was thinking.
Yeah.
Very surprising. Can you send me this chemistry material paper?
Okay.
Yeah, the last one, right? Bottom right. That's the
Yes,
one
yes.
that
So
Kirill. Wow.
actually, yeah.
Mhm.
So most of the cases I found, so it's like in the solution method or like in nanoparticle synthesis.
Ah,
So
okay.
I did not find any like solid state chemistry, like
Very
solid state
cool.
reaction.
Wow. So the
So yeah,
Kirill, the guy, last author, Kirill, one of the last authors, he's very
yes,
good. Huh? He's a very
yes,
good
yeah,
philosopher
yeah.
chemist.
I know him.
Yeah. Oh, you know him. Yeah, he's very. Partha's group knows him.
Yes, yes. So Partha and he has like very good friend.
Okay. Yeah, he's amazing. He's very strong.
So actually, I try to synthesize this compound, and like from ICSD, I found the like structure. So it show like so there is at 110 plane at like below 30 degree. So this is, but here it show the intensity is very low. But when
Mm.
I download and try to export the XY file from Mercury, so it will I think I don't know why it's give intensity very high, but
Mm.
in Vesta it's low actually. Then I actually try to fitting using Topaz. So this is
Mm.
like my I try to synthesize at different temperature. So up to like 550, the like compound is well, and like from 600 it's stuck on the carbon paper. So it's
Mm.
like very difficult to take the compound from here.
Mm.
And so I then like so still like 550. I hope for 600 also it will give like the pure phases, but this peaks I think it's because of the carbon paper. This
No, but
peak is coming.
okay. So here's my question, right?
Yeah.
If you look at it's a 20. Okay, it's not quite 25 degrees, but this peak here
Yes.
is
So this
maybe
is very
half
small.
half of this peak
Mm,
in 2 theta, right?
yes.
Is it correct? Maybe, right? You check.
Uh,
May not be. Maybe this one.
mm, Maybe
So
yeah. Mm,
these two peaks are the same for you, 30
yes.
and 42, right?
Yes.
Same.
Yes. Yeah.
So that's good. That's the primary phase. You see, even the 50 something peak is there.
Yes.
So the only two peaks are the ones that are exact. I don't know if this is exactly double of the 2 theta. So I don't know if it's the same crystal plane, which means there's some sort of ordering which maybe is not happening. That's my
Uh,
initial guess, but I don't know. I'm not confident.
No, actually in like ICSD and even in Vesta actually, so this intensity is very low. This
Okay.
110 plane. I think this is something error in my like marketing
Okay.
file or something. Even eventually it's fit very well. I'll show you the refinement data. So this is
Okay.
at 300. So there is few impurity phases. So I'll did
Mm.
not find which are the impurity phases. But I think if you saw like 550, it's like fitted
Perfect.
very well.
Mm-hmm.
550 and like 450 550. So there is
That's
like
great.
very less impurities there, and eventually from 600, so it is like the carbon peak.
Excellent.
So I think so if I using like the DJs, then maybe the carbon peak will not appear here.
Let's go, man. First new synthesis. Let's go. This looks promising, right? I
uh,
think it's
even
fantastic.
even I took the EDX, but unfortunately I cannot show here because I cannot extract the data in 7600, and EDX composition matches with like 112.
Amazing. And then how do you check for disordered? You have to fit the zip file to the disordered one.
Yes.
Okay, so that's done, right? And I think you just need to get very good data. I think we need to talk to whoever is going to the beamline next. So prepare samples, keep it ready so that who I
Okay.
don't know if Partha's group, I don't care who you collaborate with,
Okay.
prepare beamline.
Okay.
Yeah, and what else, right? That's it, right? That's the last step in a
Hmm.
way. And then you do the DJS, of course. So now you know it's 550, and then yeah. So that's the idea. And then hopefully we can synthesize it. And remember, for thermal conductivity, you don't need it fully phase pure, but it seems like you're
Yes.
very close. So that's
Hmm.
already good enough because then we send it to our thermal conductivity guys. You can prepare the sample, you can measure it. Of course, you know how to do this now,
Yes.
right? If the DGS is not great, you do SPS,
Hmm.
and then we do an EDEX mapping later. We polish it. We do EBSD.
Okay.
We send the samples to econ and we measure thermal conductivity. Okay, we know
Okay.
exactly what to do. Okay, so this
Yeah.
is looking good.
Okay.
Excellent.
And
This is what
next,
I was hoping, but the potassium freaking
yeah, I hope like if we using like potassium metal or K2T, then it will work.
yeah.
Man, I'm pretty confirmed that if we get potassium somehow, by whatever chance, we're going to make the other one as well.
Do it, man. Do it. Like this is, sometimes you lose a little bit of hope, right? Like, man, shit's not as easy as you think. But then, like, you see, like if you think carefully and if you're lucky or not lucky, but if you look through the literature, which you have done, and if the precursor is not an issue, then it works out. So so I think Jayanta has made the first bulk sodium antimony selenide. You know, now icing on the cake is low thermal conductivity, hopefully, fingers
It's
crossed.
going to be. It's going to be.
But one of the issues you mentioned, Janta, is that the calculation that they did was for the 166 or something monoclinic, or what did he
Yes,
say?
yes, yes. I think like 166
Yeah,
space
so
group,
that's
not for like 2251.
yeah. So you only made the 2 to 5. You did not make the one that they predicted.
Yes,
It's a cubic actually. 225 is a cubic.
This
cubic.
thermal conductivity, but it's interesting
Must
because can
must
you
might
yeah, if it's nanoparticle means no one measured thermal conductivity. I'm assuming no one
No,
did the
No, no,
calculation.
no, no one, no one. Yeah.
no.
So we need to, this is the feedback we need to give back to them, right? If the structure is made, now the disordered phase is given back to the auto kappa, okay,
Okay.
and calculate. Can you do one thing? This is like a plus agenda. Please present this
Yes,
on
yes,
the
yeah.
25th meeting. But before 25th meeting, you know this new guy, right? Michimasa who came in.
Yes, yeah.
Can you try to find him in the office
Okay.
and show him what you did and see you have the SIF file,
Hmm.
and with the SIF file, the correct SIF file, you think, is he able to do auto kappa calculation for you?
Okay.
Okay, can you go
Yeah,
ahead and do
sure.
that?
Yeah,
Okay, and
sure,
tell him
sure.
that we want the calculation to be done by the 25th meeting.
Okay. Okay,
Okay,
sure, sure.
man, you got me all excited now. But you see, this is so hard because the phase that they predict is not what we made, That's the
Yes.
challenge.
Yeah. Yeah,
Not
actually,
easy.
I think they will took from like material project, and but in material project this is not synthesizing. This is like theoretical.
Yeah, they have the trigonal, they
Yeah.
probably have the trigonal phase, right?
Yes.
R3 bar M, but
Absolutely.
yours is F3M.
Did you check any like using multimeter is the conductor or not? Did you check?
No, this is like a small scale, like I think
I
50
mean,
milligram
just
sample.
I mean, I know,
Okay,
I
yeah,
know.
no. I did
Mm.
not check.
Yeah, just check.
Okay.
Like, yeah.
But you're thinking thermoelectric, right, Mahesh?
I
I'm
mean,
thinking.
it's not about the like band gap. Is this compound might have high band gap?
Okay, I'll check.
Yeah, if the conductive is very good. I mean, if it is conductive any kilo ohms or
Mm,
kind of ohms is good. I just would like to see how conductive is
To
this.
me, it looks shiny. If it's
Yeah,
shiny, it's
then
probably conductive.
conductive. Yeah, I
mm.
mean, curious.
Then optical range, I think it should be okay. Doesn't
Yeah,
look like
Yeah,
too high band gap.
yeah, it could be.
yeah.
Great. Let's do the DGS and I give the CIF file to Michimasa and ask him to calculate the
Okay,
auto kappa. Okay.
okay.
Great. Okay, go
And
ahead.
now about like my compound. So actually, I refine all the composition. So like if I increase or decrease the copper concentration, there is few like other minor
Impurity.
phases there.
Mm.
So like how relevant are like so the all the trend like electrical conductivity and thermal conductivity. So this is like due to maybe the impurity also can come in,
Mhm.
right?
Of course. But do you have the, can you, in this table, this is impurity concentration.
Yes.
Where's the transport data? I think
Yeah,
it's a,
I have. So
mm,
this is my refinement. I hope this is
very good.
okay.
I don't know. Do you think it's okay? How do
Uh,
you tell if it's okay? I mean, the GOF is small, RPRW looks
yeah,
small.
I think like there is no other phases. I fine.
Mm.
So hopefully it's okay.
This is something I think you should just. Is this in this work? Is Partha's team involved?
Yes.
So ask, talk to them,
Yes.
man. They're the experts.
Yes,
They will
yeah.
make sure that they're okay with it. Okay.
So this is the transport properties.
Hmm.
So if so, I think this is because of like impurity scattering, the electrical transport will decrease and even
This
the
is
thermal.
SPS, right?
Yes, SPS. And if you saw like in case of 4.4, there is like copper telluride, like 6%.
Hmm. Hmm.
So I think due to the copper telluride, the electrical conductivity increase because like when I don't added extra 2% titanium, there is like 10 to 15% copper telluride. So
Hmm.
due to that, the like electrical conductivity at room temperature around like 400 Siemens per centimeter. So here like the
All are
copper telluride,
semiconductor, man.
yeah, yes.
Only copper 4 is
Mm,
4.4 is metal, rest is semiconductor.
yes,
Yeah.
I think this is because of like the copper telluride has like around 6%.
Yeah.
Or the second phase.
Yeah, the secondary phase and copper telluride, like it's,
Yeah.
I
You
think
you
electrical
fo-
conductivity is very high.
you found the solubility limit of copper telluride in the base compound,
Yeah.
right? After about 4.2%,
Mm.
copper telluride precipitates out.
Yes.
And then that's metallic, and that gives you high
Mm.
conductivity and reduces the Seebeck. That's what's happening, right?
Yes.
And I think what's interesting is until the 4.2, you can actually see the trend, right? So let's say you go from 3.6, 3.7, 3.8, then 4, which is close, and 4.2. So you should, I mean, Pawan, can you fit this to a Pisarenko plot?
Yep, I can do all of them.
So I think we should check where the doping level is, right?
Yes,
Because
yep.
based on this, the 3.7 looks the most promising,
So I 3.7 or
or
3.9 also should be, sorry, 3.5.
4.2 also looks promising. But
No,
because you see this, oh,
Seebeck
sorry.
is low actually.
Oh, yeah, you're right. 3.7 looks the most promising, but the conductivity is low because of scattering.
Yeah, so this, did you only sample longer time, the grain size, all those things?
No, actually, I SPS, I think
Okay, should be okay then,
30
SPF.
minutes SPS.
Man, your 3 point, I would think your 3.7 and 3.6 are very good
Yep,
chance,
yes,
but
good
your
chance.
conductivity is low. Look at the thermal conductivity.
Yes, community discuss.
Why is the intrinsic thermal conductivity low is the question.
Yes,
Is the band?
because yeah,
Hmm.
I'll tell you. I think in my next slide it should
Yeah.
be somewhere. Okay, okay, I'll go later. So
Yeah.
actually, I Actually, Mahesh told me to plot the carrier concentration and mobility versus temperature plot. So actually, I plotted for all the compounds like still copper 4, not 4.2 and like 4.41. So
All of them are
Okay.
overdosed. This is the reason why.
So
yes.
this is 10 to power 21. So 3 is okay, Kedar. 10 to 19 actually.
No, this is 10 over 21 per centimeter
That's
cube.
point
Oh,
zero
oh,
three,
right, right.
point
Point
zero
zero
Zero,
three.
0.01.
zero
Sorry,
one.
sorry.
Mm-hmm.
So
Or that.
the intrinsic mobility is low,
Yeah.
Yes.
or
So
the
that.
grain sizes are too small. What is the
Yeah.
grain
That's
size? The
yeah.
SPS.
That's what I asked question. What's the grain size? Because mobility is low here.
And for the next one, actually, it's mobility increasing. So like at 300 degrees, so with decreasing the copper concentration, the carrier concentration is decreasing and the mobility is going increasing.
That's fine. Can you go to back slide? Is 4.4, not much. You don't have low temperature data, right?
No, not a low
Only room temperature and
only
above, the
yes.
whole data.
250 and above. What is your, do you remember from the band structure, what's the effective mass?
Yeah, correct. If it's high, then
If it's
mobility
high,
will be
then
Mm,
low.
forget it. There's nothing to do.
Yes, yes.
mm, I did not. I have the band structure somewhere, but
But no, this you need this.
yeah,
No,
This is P
nothing for
type.
this.
P type.
Correct.
This P type, the band looks flat, man. Maybe the band
Yeah,
looks flat, you just have
No,
very
it's
high effective,
gamma point is yeah more broadened actually, not that sharp.
not that sharp. So you don't have
Yeah.
dissipative band. You have very broad bands. It's like an
Can you
oxide.
can you ask this who's who did the band structure
Andy, Andy.
Andy.
and ask him the effective mass values?
Yeah.
Okay.
Mm,
Pawan can help you do the analysis. If
yeah.
it's intrinsic, so the only question that remains is the intrinsic effective mass low, high?
Mm,
If it is, then
I
the intrinsic mobility of the material
will
is
be
low.
low. Yeah.
Then you're not going to get a good power factor, right? Because
Yes.
Correct.
carriers are very massive. You won't
Mm,
get good transport.
Yeah.
But
yeah.
thermal conductivity is very low. So I think we just write up, then you're done. Your paper is done.
Yes.
Okay.
Here, with the decreasing the copper content, even though it's p-type, right? The
Yeah.
copper content is decreasing. Typically, the whole carrier concentration should increase in other ABX2 materials. Whereas here, the copper content decrease, the carrier concentration also decrease.
Hmm.
This is like linked to the transport, but why is
Yeah.
decreasing? We don't know.
Yeah, we don't know.
Yeah, this. Uh,
So, is it
yeah,
possible
copper
like
is.
due to impurity or like or here actually the disorder copper concentration maybe will changing. That's
Uh,
why the because
Yeah, I ask like some theoretic guy, like defect calculations you need to do, like
yes.
when the copper occupying some positions are selenium, tellurium occupied in the copper positions, what what conditions, which is more favorable, and will it explain the transport,
Yeah, I
like
mean,
defects?
the main issue is I agree with this approach, but the defect calculations are quite expensive.
Mm,
And for disordered compounds, they're not very accurate. And
mhm.
so it's not worth it because this material doesn't have enough good transport data. Someone else can do it.
I mean, yeah, the cation deficiency typically be more p-type. This is like we need to answer. I mean, we need to say some.
Some at least have some hypothesis. So
Yeah, yeah.
you can check in literature and stuff if
Mm,
there are certain compounds and then just say it could be.
yeah,
See, I think it's a good point, but I just am not in favor of
yeah,
us
got it,
doing more calculations for this.
Uh,
got it.
no, like what I'm thinking. So in case of like copper for titanium telluride 4, so the disorder copper is there, right? So if you decrease the copper concentration, then the
Mm,
disorder copper also decrease, right?
Mhm.
So actually this is involving in like the transport property as well,
Mhm.
because if you see this one in case of like fully like in solvent compound, the electrical conductivity is very high, right?
Mm.
And eventually, so in case of selenite, so there is like even the thermal conductivity is very high, but why the thermal conductivity is very low? Because of the disorder copper. So disorder copper here, it's like a rattle in the system. So that's why the thermal conductivity is very low.
But you have to answer the question, why
Okay,
does
yeah,
the
concept.
removal of copper cause you to have de-doping, right?
Yes. So
That's
Yeah,
the question.
de-doping is done.
Usually, okay,
Mm.
adding copper vacancy should dope it. That's what you're trying to say, right? But this is opposite.
Yeah,
Why is the question.
yeah. And not
What you
only that,
answered is with respect to the thermal conductivity and the structure. But what happens to the density of states that causes this de-doping to occur? That's the question. Instead of doping, de-dopes. That's the question.
yeah, I was unable to get the Hall data for the copper 4 and 4.2. It's kind of metallic, right? Very hard. Even though I increase the current, I increase the magnetic field, I couldn't get the linear Hall. For metallic, it's damn metallic. I will try to decrease the thickness and try one more time. Already tried twice.
Yeah. I mean, is the curve for the so if you go to the mobility data, the temperature dependence is quite strong, right? Or is it just because the range is small?
Small.
Yeah, not much, not very, just 4.2. That's why I asked if you have low temperature to see the trend nicely.
That's true.
Yeah. Go back one more.
These samples should be very
Yeah.
stable, right? You should be able to run them in the PVMS.
Yes, it's like overnight 1, 2 samples.
You
It's
just need to
totally.
reload them one by one, but I think it's okay. You can collect this data slowly. We might add that to the paper later.
Yeah, it will at least give you the dependence, independence.
Yeah, so it'll be good to know the intrinsic effective mass. Is the intrinsic mobility of this sample small or not, right? The problem is that the one person who can do these calculations is Nongwei, and he's very, very, very busy. So he can do these calculations called AMSET, and
How about Andy?
Andy cannot do AMSET.
Andy cannot do. Okay.
But it may you can ask him, Jayanta.
okay.
Okay, so there's a lot of follow up for you to do. So firstly, for the other project, talk to Michimasa and give him the CIF file and ask him to do auto kappa because you're only doing thermal conductivity. For this compound, since Andy has done the band structure, extract the effective masses and give the effective masses to Pawan. So he can do the calculations for you. You can sit down with Mahesh and Pawan and finalize this. And then for that band structure, make sure you write this down or something, keep it in mind. Andy has been doing this band unfolding for your project also. I think he must have
Yes.
told you. When we talked last, he
Yes. Yeah.
updated. With the band unfolding, since he extracted the band structure, he might be able to do something called AMSET, AMSET. Okay. Worst case, I'm going to meet the author of AMSET in Boston in 2 weeks.
Oh.
So you can send me this data, send me a cleaned up version. I'll try to present something like this.
Okay.
I mean, I think it's kind of new. I don't know. I haven't thought about what I'm presenting. Please send me anyway. I'll figure out what I need to present. Okay. And I will talk to Alex. Alex is one of the authors of AMSET.
Yeah,
And
true.
I will just ask him, hey, Alex, if you want to put this through, it's a disordered compound. So it makes it a little bit challenging. If someone in his group can do it for us, that'll be fantastic. The only problem is that the thermal power factor is not very high. But I think it unlocks one possibility for us where a supercell disorder can be done through AMSET. That will be very, very nice. So I'll have a chat with him about this.
Hey, Jayanta,
Yeah.
could you go to the phase purity kind of quantification table because to understand the transport? Here, the phases with with copper decreasing, the impurity phase, CUT is no titanium tellurine. Okay, because typically the conductivity should improve, right?
Yes.
But it's the opposite. Is it because of titanium telluride phase? Because the quantity of titanium telluride phase,
Increasing.
we need to think in this line. We'll see. because of titanium telluride is more than
Yep.
yeah.
Yeah, so there
Yeah,
is like
yeah,
excess titanium telluride, so it will, I
yeah, yeah.
think, take him
But
out
then
from the
what will
system.
yeah, this is what is nothing but titanium and tellurine deficiency. Nothing but is copper, even though you literally you decrease in the copper deficiency, but it's not copper deficient compound.
Yes.
It's a
Yeah.
copper rich compound because of titanium tellurine is separated, is not participating in the main phase. So copper rich is more in 3.6 compound compared to 3.8 in that way. Let's think about it. Yeah.
Can you quantify some way, like maybe
Yeah.
XPS or something, to give the intensity is increasing something?
Can you quantify the pure phase? Pure phase already quantified, right?
Yes.
98, 96, 95. Uh-huh. Mhm. Still the
This
pure
is very
phase.
nice.
I don't know. Is it titanium? Did you check titanium telluride by alloy? The binary compound of titanium telluride is
Uh,
N-type or P-type or some?
no, no, I did not check. I'll check.
No matter. I mean, no matter whether it's
Yeah.
N-type or P-type, the kilograms will always add up. Okay. Expected initial drop. Mhm.
Okay, really nice work. What's
Okay.
the plan? So 2 weeks later, I check with anything else.
Yes. Uh, so actually, for like sulfur-based compound, so like it's not fully came up with like in the cycle. So
Yep.
if you see like any solvent kind of system, so in cycle like at low temperature, so it will not exactly match. So so initially I took like still 200-degree data, like at 200, then I take the cycle, then it is like, so it's changing a lot. But if I go like 150-degree, so it's like it's come up with same data. So what I'm thinking, so I'll just take like still 150-degree from room temperature 150 and do cycling.
Mhm.
Yeah.
So I think it's okay, right, Mahesh?
Yeah. I mean, we discussed.
Yeah. Yes.
Um, this is like reverse cycle, right? Maybe the
Yes.
phase is just separating above particular temperature. So it's not so to avoid the we should show only the data until that temperature only where
Yes.
there is reversal happen. Kedar.
Yes.
Yeah, I agree.
Yeah, because you already have temperature dependent the synchrotron
Yes. Yes. Yes.
data, right?
Yeah. Yeah.
So the phase is evolving. So we don't
Yes.
want to go the transport to you
Yeah.
cannot explain with the mixed phases.
Okay.
Yeah.
Yeah. And actually, I try to. I think I try like without 2%. So without 2% titanium, so there is more impurity phases. Is there? And
Yeah.
even Kedar told me to like added extra telluride. So I actually changes the telluride concentration as well as copper, but still I'll not get the phase pair compound in that case also. So only the titanium concentration change will give the phase pair compound.
Yeah.
Amazing.
Yeah.
Beautiful.
Do you have the data of without cutting with solvent and without solvent?
Yes, so it will not changing. I think it will change like 10 or 10 values, like the
Not much
yeah,
percentage.
not much per percentage.
Okay.
So it's
Uh,
almost same.
Last time we mentioned there's some absorption of solvent right while cutting.
Yes,
So
yes.
I asked you to go to do the transport without using solvent.
Yes,
Then
I'll check, but it will not change too
yeah,
much.
yeah, it's
And
fine.
I think this part better to explain like Haiwan actually took the TM data for my compound. So I think so he just gave me in the morning.
Hmm. Can you
Haiwan,
zoom?
so do you want to
Yeah.
explain?
So can you just zoom it
Zoom,
in to
yeah.
Yes.
like AB? Not play. Maybe just zoom it in. It's a bit too abstracted.
Go
Can
back
I
to
zoom in?
PowerPoint and zoom into the images. That's what I
Yeah.
do.
Yes.
Some more zoom.
So Jenta, which sample it is? Is it like some doped or not doped? I
No,
think
no.
it's undoped.
This is like
The pure
the
phase.
pure phase.
Via
Yeah,
UHS or
dope.
BJS?
Yeah. Yes, it's like phase pure, like 2% titanium added.
Oh, sure. So actually the crystallography from TM we cannot
These are very small grains, man. No wonder your mobility is low, huh?
So let me, is there a pointer or something I can use? Oh yes, I can just draw. So first of all, so from the bright field TM images, there's three different regions. You can see a lot of like small grams, about 50 to 5 to 50 nanometers. And if you just zoom in, Janta, can you really zoom it in to one of the orange circle region? You can see a lot of like these high contrast areas with bands, and typically this indicates like stacking faults within these regions, and it's very apparent within all different small regions. The SAED also indicates that it's like a polycrystalline material, but unfortunately, the structures between the rhombohedra and the cubic phase are too similar, so both of them fit, and it doesn't make sense for me to present too much. Who is it for now?
What is
So
SF? What is SFs?
stacking faults,
Hmm.
SFs, yes. So that's the information we can get from the first row, and let's go down to the second row. Yeah, the second row, zoom in a bit to high resolution TM pictures. So you can see that by the FFT, no, above, yes, above, go above, yes.
So, one quick question. This is SPS samples?
No, no, no.
Uh,
This is Juliting sample, like UJ sample, the small scale. Yeah.
Hmm.
the powder-based samples is
Yes.
not something cut
Okay.
from our meeting.
Hmm.
So you can see that most of the areas, they are like a single crystalline with a spot. And they can be indexed actually. So the result is slightly different from the single crystal XRD and synchrotron data. So I analyzed all these three FFT patterns, and actually none of these FFT patterns fits either the rhombohedral phase and cubic phase fully. And I was thinking it's locally, it's probably something in between. And what you see from the diffraction is more like probably an average of everything. That's my assumption. So for this phase, I'm not able to resolve what they are because it's too small, and structure resolution at this scale is still very, very challenging. And it also doesn't make sense to do so because maybe each of the small grams are slightly different. So that's my interpretation. And of course, I can just fit it to one of the zone axes forcefully. But of course, the intensity doesn't match, the position still match. So I can still forcefully fit it to one of the zone axes. But in reality, is that both of them can fit, but not fitting well. So that is the high resolution TEM and the FFT, what it's telling us. Let's go down to GHI. So this is the inverse FFT from the high resolution TM pictures above. So by doing this process, it is able to tell us what are the, so these high contrast areas like this, or like this. So this doesn't follow the single crystal periodic patterns. So when they don't follow, they indicate defects. And if I go into these places, look closer, or if I can just calculate the Burgers vector, either methods can work. So we will find that this region G is very rich with screw dislocations. This region H is very rich with mixed type dislocations. And this region I is very rich with both edge and screw dislocations. So that is the observation from all the three high resolution images and the RFFT. And Jante, if you can go down. So the EDX mapping, I think, is self-explanatory. I don't need to expand too much. So, and that's about a Janta sample. And if you compare Janta sample against the solid state sample Janta also sent me, you can have a very clear feeling that the crystallite size is not in the same scale.
Which
So,
sample is this? Sorry.
so this is the conventional solid state synthesis sample.
Oh, you made it through conventional synthesis also.
Yes.
Janta
Yes.
made it.
Yes.
Also 2% titanium.
No, no, no. Without 2% titanium. So
How
actually,
did you do this?
no, actually, so during my vacation in ID Kharagpur, so actually, so without, so it's like not fully phase pure. So we took like few crystals and like few like phase pure crystals, and then here I bring with me, then do the TM.
Can you get them to do, or you're going to go for holiday, right? Can you do more 2% titanium, see if we get phase pure over there?
No, actually they tried, but it will not. Yeah, I already tried.
You already tried, doesn't it?
Yes.
So it's not just the 2% titanium, it's also some kinetic
Yes.
synthesis
Yeah.
out that stabilizes.
Also.
But okay, for me, it then begs the question, why your thermal conductivity is not super low? Like if you look at the first figure, like man, I would have expected like even smaller, zero point 0.2, zero point 0.3, I guess it's crazy. But the electronic part is not super high either, right? So
Yes.
it's kind of surprising.
Yes, I was very shocked when I get
Electronic part is
or
not high because the sample is you don't want to center at very high temperatures because of phases evolving. The centering only the temperature is very low, like 200 or 250,
It's 200.
Hmm.
200. The centering temperature is only 200. Means the grains are really, really small.
No, but this is not even cinder. I'm talking about
No, no.
that's why the electrical
Yeah,
conductivity.
yeah, yeah.
maybe Kara, do you think it makes more sense to let Genta cut the sample? I mean, this is on powder, man. It's not the sample you are testing.
But that's SPS sample, right? We can,
Yes.
but I don't think we get anything new. Maybe it's worthwhile, right? If you can do that, Jayanta. Is it easy to cut the SPS samples for TM with FIB?
Mm,
That need Chen Guang's expertise. He is better than me.
Or like you pay like something like what I
Yeah,
think
I'm meaning. I
I
mean, I
million,
can just
right?
cut it. Previously I cut for Chen Guang, but he is not satisfied with
Mm,
the quality, and then he sent it for I think the iron milling process.
mm-hmm. No, this one FIB cut should be enough because the SPS samples FIB cutting should be sufficient.
And then I just do it. It's pretty
Yeah.
straightforward.
The AGSBT2 is very brittle and difficult, but this one is not. I think it should be okay.
Cool, cool, cool. I just give it a try.
You give it a try because
It doesn't
also
harm.
like I'm just imagining the reviewers asking the question, then say if they try to link the transport to the microstructure,
Yeah.
it might be good. I mean, we'll do. I think you should do EBSD for sure. Look at the grain size of the SPS,
Uh,
um, but also then look at a TM sample.
Jayanta, can you
yeah.
choose one compound? Now you already from increase from 10 minutes to 30 minutes, right?
Yes.
Like neon pound also like same. The grains are small, right? At
Mm,
200 itself,
mm.
high pressure, and increase one sample for 2 hours or 3 hours, just 2 hours. There's some limit in SPMS, SPS. Can you do 2 hours and see whether really the conductivity improves or not? For one sample at least.
Okay. So actually, conductivity is does not affect too much. Actually, I already did.
Did you check?
Yes. Yes. Yeah. With increasing
Okay.
the temperature, it will not increase too much or decrease.
Dual temperature. Okay.
Yes.
Okay, my feeling is we can go very dig deep and all this stuff, but
Yeah, but we need to finish it.
is the mobility intrinsically low or not is the key question. Thermal is still pretty low, zero point 0.6 points is pretty good. So if we can get to a regular semiconductor level, and this is
Yeah.
clearly a semiconductor, zero point 0.4 EV band gap, we need to think about what we need to do to increase. So if Mahesh's point is true, maybe we might be okay with annealing, compressing under slightly higher temperature, higher temperatures is okay to have phase small amount of impurity. But
This suggestion we gave last week.
Yeah.
Did he try at high temperature? Other also, even
yes,
though some pages there. Did you try SPS?
No, not at like high temperature. So actually,
Mm,
I try to using like increase the time, but the value is same.
okay, no, not this one. Gather also last week, last meeting also we suggested, even though don't worry about the other phase evolutions, try at high temperature one or two samples to make it
more
like
conducting.
more grain, large grain.
Yeah.
Like yeah,
Your CVAC won't change. I mean, it might
no, it
change.
may change. Yeah, I
It
mean
might change.
impurities. Yeah.
I would focus on your 3.7, 3.6, and 4 samples.
That's
First
what.
one sample, we will see at high temperature, like what is melting temperature is okay, 500, 600, where TGA.
Yes, I think 500 still like 450, 500. Okay, not 600. I think
I
maybe it's
mean,
melted 600 something.
okay, then no, five. You need to be 100 less in SPS
Then
because
500.
under pressure, right? Yeah, then 500. Try 500, 30 minutes, one sample. See, is the grain size change and is deteriorated fully or okay to improve the property?
Yes, but like then there should be a few minor phase, right? Around like
Yeah,
5 to
yeah,
5 to 10,
they
10%.
definitely they have some phases, impurity phases. Don't worry about impurity phase, whether they really deteriorate the property or not. We don't know. Let's try with one sample.
No, but like so if there is like more copper telluride, then they definitely affect the electrical transport and thermal transport, right? So it is increasing.
The 6% will increase more. The 6%
Yes,
of CUTE, whatever you predicted
yes,
impurity
yes, yes,
phase.
yes, yes. So in case of 6%, the value will increase, right? Let me show. Yeah. So the value is increased, right? So it's like 1 point. So if I space more, the value will go up. I think more
No,
than 1.5 or something.
take I mean not that compound. Uh, Choose 3.6.
3.6, 3.7, and 4 are the three ones I would
Yeah,
choose. 3.6, if you look at the CBAC, right, it's in the right range. Even if the doping alters, it might go lower or
yeah,
slightly higher. It's still okay,
yeah.
right? Same with 3.7. Then you're hoping that 3.7, there should be some de-doping. If the de-doping happens, then it'll go up also, the CBAC. So you're in the right range of the CBAC, and the doping will change slightly the CBAC, hopefully, if
Yeah,
there's doping occurring. Those are
yeah.
the
Let's
samples I
see
would
one
prioritize.
sample. Yeah,
Sorry?
yeah, yeah. Better to try with 3.6 and 3.7.
3.6, 3.7 would be my guess. Okay.
Yeah,
And already the thermal is already the lowest.
but thermal conductivity may improve, may I mean may
Increase.
increase.
Yeah, I think
Yeah.
it's definitely increased, right? So
But
because
I mean, let's see the overall performance. If conductivity improves and the power factor is higher, then the
Conductivity, yeah, I see the conductivity should go up by a factor of 3 or 4.
Yeah,
Okay.
then that will benefit.
Yeah, and then thermal conductivity, even if it goes up by 20 to 30%, it should still benefit you because the thermal conductivity is lower than 1. So you'll get to some
Mm,
reasonable ZT, man.
yeah,
yeah.
But I feel like the story is not about ZT. We've
yeah,
like,
yeah, yeah. It's a
Mm,
phase pure
yeah, so the
compound.
phase pure, and then we do the, and then we just show the low thermal conductivity. I remember I wanted to ask you, Jayanta, we asked Longway to calculate thermal conductivity or not for this?
yes, I asked. So actually, he told so there is like it will take like 2 weeks or something. So he tried like one structure first, and then he just let me know.
Yeah, it'll take him some time. He's very busy. He has a lot of
Yeah,
things to
yeah,
study.
he actually. So without Nongway, like anyone can do this, no?
The
I
new guy
think
came,
same
right? The
same Michimasa. Just
yeah,
ask Michimasa same thing.
Okay,
Ask him both.
Michimosha.
Ask him to do auto kappa on two compounds.
okay,
The sodium antimony selenide and this one.
Yeah.
Okay.
okay. I think that's it.
Good work, man. I think you earned your holiday, Jayanta. I was giving Jayanta a hard time when we got together for beer. But now he brought all this data, so now I think you can go.
Yeah, but actually we need to finalize like like we need to at least do it very fast. So maybe like
Yeah, so the main thing is the effective mass. If the effective
yeah.
mass is high, then I think it's okay. Your intrinsic mobility is
Mm.
low. If that's the case, then no matter what you do, it doesn't help. Then you
Yeah.
need to do the SPS, what we talked about, 3.6, 3.7. You do high temperature and then measure the transport. Let's do those two things. And I think we'll make a call and we'll finalize.
So at high temperature space, so so why we need so because of like improve the ZT or something?
Your grain
Grain
sizes
bar.
might increase. Your mobility might be low because it's not intrinsic. It's limited by the
Mm.
small grains because low temperature SPS should not give you very
yes.
high
Yeah,
grains.
grain the
Okay.
issue.
Already SPS gives you a few micron grain size only at high temperature. So if you're doing 200 degrees Celsius, your grain size are probably off the order of the electron mean free path.
Yes.
10 to 20 nanometers. 10 to 20 nanometers will scatter like crazy, especially with
Yes.
dislocations. Electronic
Yeah.
mobility is killed. So you're not near the
Killed.
intrinsic limit.
Yes. That's
This is the
problem.
logic.
Mm.
That's it. I mean, those are the last two things, and then you can go. And then let's finalize and we submit. We'll start writing. This one we can send to NatureCom.
Okay.
Where do you want to send?
It's up to you. I don't.
I don't know, man. I think NatureCom.
Okay.
I don't think it's good enough for nature synthesis, nature materials, because the ZT numbers are not high, but it's phase pure. But I think there's a lot of things, nice analysis here. So, and is there any synchrotron stuff coming? I think it might be good to have some synchrotron data for this
Yes,
compound.
yes, yes. Synchronity we have.
Then we try NatureCom. Advanced materials, NatureCom, something like this.
Sure.
Yeah. Okay. Anybody else? Thanks, guys. You think you want to present something?
Yeah, I can update some data here.
Okay.
Let me present. Yeah, can you see the screen?
Yeah, it's coming. Yeah.
Okay. So basically, we were currently doing the heavy dope samples which is used for the machine learning
Mhm.
optimization, and I think they are using the EGBO optimization, and so currently we're doing these 4 recipes, and which like doped with different amount, a large amount of bismuth, antimony, and silver, and along with the aluminum and yttrium. But
Mhm.
the yttrium one seems with very low ZT value. So let's see. So we compare it with the previous germanium telluride like samples. Like is electric conductivity is relatively low because of the large amount of the trivalent dopants. Yep. And I think for the 30% silver one, I think the CBAC is in I think it's in a good regime, like at the high temperature. It's like 180 or something. Yeah.
But the power factor is low.
Yeah, the power factor is kind of low. And we do SEM, so we can see that in the 30% antimony dopant, the antimony and the bismuth were relatively like non-uniform distribution. But for the 30% silver, we can see here. So I think it's already reached its solubility limit. So it will form this cluster, like very bright colored cluster. So I try to this is Chen Guang's idea that we can add a few more tellurium to the especially to these 2 samples, because for the like the 10% aluminum one, the sample is not like it will like break after DGS. So we have to do SPS for this one. And for the 10% yttrium, you can see little chunks of yttrium on the surface. So it's not with high solubility in germanium telluride. So we try to add 1% of tellurium in these 2 recipes. And we can see probably because 1% tellurium is too high because I think it's in the underdoob regime. So the CBAC has a peak over like 600 Kelvin. And the power factor is still relatively low. And so for these 4 recipes, I think the 30% silver has reached a the relatively high ZT. over the high temperature. But the thermal conductivity is still like still need to measure for the 1% like tellurium to see if that will like improve the high temperature ZT.
Okay, so I mean, I think it'll be so let me. There's a lot of data here. So before analyzing everything,
Yeah.
let me ask. So who you are working? This guidance came from, was it Andre and Pepe's code?
Yeah,
Or,
yeah.
is that right?
Yeah.
Okay, and then the goal is based on the machine learning predictions. There's some power factor predictions. So the goal is to try to match and see. It's not necessarily just high power factor, but to
Yeah, yeah.
match the predictions, right?
Yes.
So can you please work with Andre and Pepe
Yeah.
and present this full story? Okay.
Yeah.
Also, I think anyway, we will chat later today with your plan and stuff, but we will then think about more logically what's the next step, right?
Yeah.
Seems like we've done a lot of, I think you've been doing this quite a bit. So I need to get a better picture of what's going on. Okay. So
Yeah.
the numbers are not bad, but it doesn't really beat what has happened in germanium
Yeah,
dialect before, right?
yeah, 2.4, 2
Yeah,
plus to 2.4.
very hard to do that. I mean, thermal
Mm.
dialect is already very low.
Yeah, I
So
think it's all about the power factor.
which is crazy. So
Mm.
it might be good to do that, like just sit down, say with Pepe. Um, so you've been doing these experiments based on the machine learning predictions already by
Yeah.
yourself. Is that what's happening?
Yeah, just they give me like this for recipe supposed to like have like good like predictions.
Okay.
So I'm currently doing this, but seems like especially the 10% Ethereum did not like perform very good.
Mm-hmm.
So like maybe you stick to silver dopants,
Yeah.
like 30%. It seems like really good.
Yeah. What else can we do there? So you added tellurium already. That's why
Yeah,
I'm trying to get a good
I
feeling
think the
for.
tellurium may be too much, like 1%. So
Mm,
and maybe we can reduce the amount of the silver because to see like
mm-hmm.
because there is
Yeah.
no yeah.
So are you working? Is Chengwang helping you with this? The
Oh
thinking
yeah.
and okay. So why don't you talk to him and see what does he think are the next few experiments to do, and then send me a summary of this data, like the whole picture. Okay, I don't just want the like data. I want to see what are the machine learning predictions.
Yep.
How did you choose the matrix of compositions and stuff?
Okay.
And send it to me by like the end of the month.
Okay.
Okay. And I'm going to meet Pepe when I'm in Boston.
Okay.
I will have a chat with him to see what is he thinking, and then I'll
Yep.
let him decide what to do with this. Okay.
Okay.
And then yeah, let's chat later in the evening. But yeah, good job. I know you had a lot of trouble with the cutting and stuff, so all that is sorted now.
Oh, we're just using the SPS for most of the
Okay.
sample, but the with large amount of silver, it seems fine. Like the 30% silver, the sample seems fine for cutting, but the others is not.
I see.
Yeah.
30% silver, you think even the DJS samples are good to be cut.
Yeah.
But this 30% samples is a lot of phase separation. Like the silver is like agglomerated, right? If you look at the EDS, do you still think it's good samples?
No.
Yeah. So like the data is the data, but
Yeah.
it's not. So this is the, see, Jayanta, for example, look at the transport, right? This is
Yeah.
clearly not phase pure, but it's the best thermoelectric data. Sort of what's going on. Like thermoelectrics is weird like that.
Just saw that.
No, Kara, I don't really believe that. So a lot
Different.
of time in EDX mapping, it just exaggerated the contrast. Maybe
Mm,
the dark point here is only like 2% away from the bright point.
I see.
So you need to see the raw data.
Okay.
It's just I mean, it just scaled.
Okay, then please check, yeah. I think this will be good to check. Okay, so I just want to get a better picture of what's the plan with this. Yeah, you think?
Okay.
So then
Okay.
I will, if you can try and have a chat with Pepe and see, give him the and Andre and say, what is the goal of this? Then
Okay.
first put your thinking to it. Then
Yeah.
have a chat with Cheng Wang to see what he suggests. Then we think of a few more experiments to do, and let's try to see if we can write it up.
Yeah.
Yeah, because
Okay.
I think there are other projects which can use your expertise. So if this is done, then we can explore what else we can do, right?
Yeah.
So that's sort of what I'm thinking.
Mm-hmm.
Great,
Okay.
lots of learning. Well done. Okay. So quick question for Christine and Delvin. Are you guys? I mean, now we don't have the kappa gen synthesis, right? So what do you guys focus on? Can you quickly walk us through what you're doing?
I'm making figures for um thermocatalysis, so XRD and then XPS.
Mhm.
Yeah, for the supplementary figures.
Okay.
I've recently just worked on improving the DJs. So I've recently gotten a new IR sensor. So now it can measure down to 50 degrees.
Awesome.
So from 50 to 1800 degrees. So now we can, well, we can control some of the ramping rate going up, and you can measure lower temperature as well.
Okay. Well, one of the reasons I'm asking, that's really nice. One of the reasons I'm asking is I spoke with Amol, and I think in December they should have 3 plates ready for putting inside the HT reactor. Okay, so one plate is fixed, right? Because already you synthesize the samples and they will put that in. One more plate, especially Christine, if you talk to Pepe, he needs to send the A lab samples, the ones he synthesized. So that's another plate.
Mm-hmm.
But we have one more plate left, right? Which he thinks he can run in December. Which means what I've asked Andre to do is to take the existing data, analyze it, and come up with some predictions. He says he's almost ready. He might we can on Thursday we can chat about this. And I don't know what you guys are thinking and your schedule is. But if you're able to do 14 more synthesis, Soumya will be back in the first week of December, so he can also help. And we try to do one more batch in the first week of December, or first and second week of December. That'll be fantastic.
I think we can do it.
I think we should definitely synthesize the better machine learning samples.
Yeah. The main issue is the machine learning, because we don't have the data from the 14 more samples, right?
No,
So that's why I was like, but anyway, we have time, so we might as well get more data, right?
you might as well. Yeah.
So that's the plan. So I think Andre will work towards. So in your schedule, please plan. So in about 2 weeks or so, we'll start with more precursor preparation, and in the first 10 days or something of December, we prepare 14 more samples and hand them over so that Amol can run it. So we'll finalize this on the Thursday meeting. Okay.
Sounds good.
And Devin, if you now we understand the magnetic stuff. I mean, you know that Joel got rejected, but we'll have the review. Ivan is on the thing as well. But it'll be good if you have any small bandwidth to try to just think about that iron, it's the magnetic material. What I'll do is I'll connect you with the startup, right? And let's just take the discussion forward now that our own initiative is kind of stalled. So let me connect you to the MatNext guys, and let's see, you can just continue the conversation there to see if there's something we can do with them.
Sure. Yeah. Yeah. Let me know. I'll talk to them.
Yeah, I'll arrange by email.
Sounds good.
Okay, great meeting, guys. Lots of nice stuff. Ivan and Christine, I think you're meeting with the lady Thursday, right?
Yep.
Yeah. So
Yeah, I know the lady.
Oh, you know
So
her.
he previously came to Bears because we also signed a contract with her in Bears. So it's the second meeting already.
So she's not keen on doing something or what?
What I kind of feel is, say, an extensive list of Sigma. He might not be the person to give the full right or full permission to give you the full list. So I kind of feel like the way to do this is I need to chat with her and then to give her like the importance of what we are doing, and also like the systems, say the automated ERP, which they may be integrating on us and other potential customers. So that's what I'm thinking. And so she is able to up level in sigma.
Yeah.
She
I mean, I
might,
think so try to give her this analogy that
yeah.
in small molecules,
Mhm.
this idea of retrosynthesis is quite advanced because sigma Aldrich's all the precursors available are then automatically available for everyone to look at, and they
Yes.
can put machine learning models. But we don't have that for inorganics. So I would recommend starting with like 10 elements. Don't go like 50, 30, you know. I think the original was too exhaustive.
It was
Start with
too
like,
exhaustive. Okay.
yeah. Take the relatively easier one. Like look at the sodium antimony selenide that Jayanta made, right? It's like stuff that's easy.
Man, this is difficult. The sodium antimony telluride is difficult. This one was because Chen Guang and me, we luckily bought some sodium.
Oh yeah. But I mean, what my point is, you stick to a few. Like okay, sodium might be difficult, but antimony, selenium,
Yeah.
metals are easy.
Yeah.
So you start with those easy transition metals, etc., and then you know say we need a CSV file. I don't ask her for like access to the blah blah blah.
No, we just need a CSV file.
Just say, look, just give us two row, just one row of all precursors that you can source and supply to us within the next month. That's it. And the
Yes.
vision is that we will build it and tell us what you want in return, right? And then
Yeah.
and also say that I'm happy to chat with whoever in their team to discuss further.
Yeah, that's our target. And maybe so in case they want to meet you, I will also put you in the link.
Yeah, please do
Yeah.
that.
Yeah.
Great. Thank you guys. Take care. See some of you in 1 hour.
Yeah.
See you guys soon.
Bye bye.
See you. Bye.